Okay, so let's continue a little bit. So we talked about pulse amplitude modulation and so forth. And then, so that's the physical layer. Moving up a little bit, or actually this block codes and things like that, that could be used for error detection or error correction. So if you remember from the Shannon block diagram, there was a channel encoder and channel decoder, and these can be based on these block codes also. But in the course now, where we have talked about block codes, we have used them mainly for error detection purposes. So the idea is that we have some data bits here that we would like to somehow protect, in the sense that we would like to add some information to these bits, such that we can detect if errors have occurred at the receiver. So the idea is to take k, small k information bits and put them into this encoder, and then we get n bits out. Okay, so the number of output bits n is greater than k for all practical block encoder. You can have n equal k, but then it's useless. Doesn't help you anyhow. Right, so n is typically greater than k. So the input bits are called the information bits. If we block them into this vector, then it's called the information word. The output bits are called the coded bits, and then they collectively are called the code word. So this is the code word, and this is the information word. The code is the set of all possible outputs from the block encoder. So that's the set of all possible code words. And since we have k input bits, we have 2 to the power of k possible input patterns, which means that we have 2 to the power of k possible outputs, which means that the number of code words, distinct code words, is 2 to the power of k. Code rate is the ratio between k and n. And if you want to have a unit on that, is the number of information bits per coded bit. In practical systems, we almost always use systematic block codes, or systematic codes. And these are of a special structure. The code word here consists of first the input bits to the encoder. So this is the information bits. And then there are some check bits or parity bits. And the reason why we use systematic codes, there are many reasons. Or the prime reason for using it is that it's very easy to go from code word to information word. We simply just take out the first k bits of the code word, and then we have the information bits. Okay. Otherwise, if we had some generic function going from D to C, that might be difficult to invert. But for systematic codes, it's very, very simple.
I have a question.
Yes.
The code, is it C1, C2, C4, or C1, C2, C3?
So it's 1, 2, 3, 4, etc., up to 2 to the power of k. So yeah. So if k is equal to 3, then we have 1, 2, blah blah blah, up to 8. Yeah. Hamming weight is the number of ones in a pattern. Okay, so the Hamming weight of U is the number of ones in U. Hamming distance between two binary vectors is the number of bit positions where these are different. So the Hamming distance between U and V is the number of bit positions that are different in U and V. And we can calculate that by taking the Hamming weight of U plus V, where plus here is binary addition, or XOR, or modulo 2 addition. Okay, so which means that, for instance, that 1 plus 1 is equal to 0, okay, which is 0 plus 0, and 1 plus 1 is equal to 1 plus, I said 0 plus 1 is equal to 1 plus 0, which is equal to 1. Okay, Minimum distance of a code is the distance between, the smallest distance between two distinct code words. So physically, if we had the code words, you know, in some space like this, there are two code words which are closest to each other, and that is the minimum distance. Okay. In now Hamming distance. Right? If C is the transmitted code word and the received pattern is C plus E, then E is known as the error pattern. So for each position in E where E is a 1, that corresponding position in C is in error in Y. Okay, so we take C and we flip the bits according to E, and then we get Y. So the number of bit errors we do here in the code word is the Hamming weight of the error pattern E. Okay, why is this important? Well, okay, it follows here. So receiver declare that no errors have occurred if the received pattern is a code word. So when we do error detection, we need to observe Y. We observe Y. And we know that Y is equal to C plus E. This we know always the case. Okay. Now, if Y is a code word, that is, it's in the set C, then we say no error, right? Because it seems to work, right? If Y is equal to a code word, then we say things are okay. If Y is not a code word, then we are for sure that an error has occurred. Okay. Why is that? Because we know we transmitted a code word, and if we don't receive a code word, that means that E cannot be 0. Okay. If E is 0, no errors, then Y is equal to C. Okay. However, if we know that Y is a code word, that doesn't imply that E is equal to 0. So sometimes we let things through, that is, we declare that Y has no errors in it, but indeed it had. Okay. And that happens when E is such that E plus C is a code word. That could happen. Okay. So C is the transmitted code word. So we say that E, an error pattern, is detectable if C plus E is not a code word. And we can detect many. Okay, so for a minimum distance d-min, all error patterns with weight which is less than the minimum distance are detectable. We know that for sure. But we can also detect many, but not all error patterns which have weight which is greater than minimum distance. One can draw up a plot of this to see that this is the case. So what is a good code? Well, a good code has high minimum distance, high rate, because then we don't add so many parity bits. And then, of course, it needs to have low encoding and error detecting complexity. So the signal processing involved in that should be small. And then it should also be good in the sense that it can detect many likely error patterns. That is, patterns which have also those errors, patterns which are greater than the minimum distance. It would be nice if we can catch as many of those as possible. Codes in common use are singleton parity check codes. I'm sure you use that in the project. But then there is also the internet checksums and CRCs. Both of these have been treated at the exercises. This is pretty bad, this is somewhat better, and this is the best. This one is the most expensive in terms of computations. And this is a little bit better, and this is the easiest one. Okay. So, which one to choose depends on what you value the most. Okay, ARQ protocols. What are those? Those are there to clean up errors that occurs in transmission. So ARQ protocols are used to provide a service that deliver packets in order, without errors, without duplication. And then we can do that with some basic elements in an ARQ. Error detection codes, we need those. We need sequence numbers. We need acknowledgements, special control frames from the receiver to the transmitter. And we need timeouts. So these needs to be combined in a good way. The basic protocol is that we accept service data units if, okay, so we have a send window, so which is our buffer. Okay, so this is the send buffer. So suppose it has a space for 3 frames. So when we get a service data unit from above, we put that into the buffer and then we transmit it. Okay, and then we have a specific sequence number for that. So suppose that was 0, and then this is 1, and this is 2. And then we start a timeout. We update the sequence number, put the frame in the send window, and then we send the frame and start the timeout. And then if we get lucky, we get an acknowledgement back, which means that this frame has been received by the receiver, and then everything is okay. And then we can release that buffer, and we can accept, we forget about that. And then we can move on in the send window. Okay. If an acknowledgement, okay, so suppose then we have here frame number 1, we transmit that and we wait and nothing happens. Then after the timeout, we transmit it again and we wait, and if nothing happens, we transmit it again, and eventually, hopefully at least, we get an ACK back, and then we release that buffer space, and then we can move to the next one, or we have a bigger space in the send window. If we have a send window of several frames like this, we can have several of these going on in parallel. So that's the advantage of having a send window which is greater than 1. Receiver maintains also a window of a number of frames. Say maybe it has 4 frames, I don't know. And here it puts in frames which it receives. It knows in which order they should come, and these are placed then in which order they receive. And if we receive, okay, so we have sort of time along this axis, meaning that this is the oldest one, this is the next oldest one, and so forth. And when we come to a situation like this, then we know that we can deliver those to the layer above, because then we can deliver them in order. And then we can slide the window to start at this point. So we add some buffer space at the right here. Okay, so that's the basic principle here. Stop and wait, we have send window, receive window equals 1. Go back n, we have a send window which is greater than 1, receive window which is equal to 1. Selective repeat, we have both of these windows are greater than 1. And then there is some logic associated with this. Yeah. Okay. Which one should we use? Stop and wait is very good as long as we don't have a large delay bandwidth product. If we have a large delay bandwidth product, we want to go with go back n. If we have go back n and a lot of frame errors, go back n is as bad as stop and wait, and then we want to go to selective repeat. Okay, so that's basically how we want to do it. If we have something where the delay bandwidth product is small and no errors, by all means go with stop and wait. No need to do something advanced when it's not needed. Medium access control. It's a sublayer just above the physical layer. Okay, so we have physical layer here, and just above it is the medium access control layer. The protocol here determines how to share a common medium. So if we have several stations that communicate over, say, a radio channel, then we need to take turns or somehow coordinate transmissions so we avoid collisions. So that's how to share the common medium. MAC protocols can be divided into static channelization, long-term assignment of channel resources to users, or dynamic, where we assign resources on demand. Static is nice if we have well-defined users that use the medium with the same data rate always at the same, very predictable ones. Dynamic is nice when we don't have that, when we have users. Sometimes they have a lot of data to transmit, sometimes not, and so forth. Users come and go, back and forth. So in data communications or internet traffic, whatever, we use dynamic MACs typically because they're more efficient in that way. Random access example here is, okay, dynamic MAC could be either structured, scheduled, or not so structured, random. Typical random access examples is ALOA, slotted ALOA. Very simple, close to stop and wait. Transmit a frame, start a timeout, wait for an ACK. Timeout expires, back off, wait the random time, and retransmit. Super simple. Okay, but not very efficient. Delay bandwidth product is again a key parameter. Coordination of the medium requires using bandwidth. So when the delay bandwidth product is large, then we have problems. And difficulty coordination also increases. So yeah, that's just the way it is. Carrier sense multiple access is an improvement on ALOA. And the basic idea here is that instead of just transmitting when we have data to transmit, we sense the channel. Sensing the channel is listening to the channel. So carrier sense multiple access is listen before talk. So if the medium is idle, then we transmit. If it's busy, then we need to back off. So wait a random time. So we can do that in different ways. There is persistent, non-persistent, and p-persistent. I won't go into the details here, but there are different ways of handling backoffs. CSMA in general works well when we have low delay bandwidth products, but then worse than ALOA for sufficiently large delay bandwidth products. So again, it's almost like stop and wait and AR selective repeat ideas here, that the simplest solution is actually a pretty good solution when the delay bandwidth product is large. But was the opposite actually in ARQ. So, okay. Sorry, it got confusing there. That was not my intention. We can do collision detection sometimes, and that depends if we can listen to the medium as when we transmit. And if we can do, then we start the transmission and monitor the medium. If a collision is detected, then we abort it. So we stop transmitting. Collisions are made short in time, which means better throughput. So that's the idea with collision detection. Reservation protocols is scheduled. So this is scheduled access. Transmissions are organized in cycles. So a cycle starts with some reservation slots like this, where people or stations agree upon in which order to transmit and so forth. And then there come some data frames. And the data frames are typically longer than the reservation. So this is reservation, and the blue is data. So this is a complete cycle, and then it repeats itself with some reservation interval, data transmission interval. We can also use polling. That is, we send a polling message to users to figure out whether they have user data to transmit. Channelization. We can split the channel resources in time or frequency. If we split it in time, it's called time division. If we split it in frequency, it's called frequency division. That was not rocket science, but that's how it is. We can also use code division, which is close to rocket science because it's kind of weird in the sense that we are having two signals which overlap in time and frequency, but still are completely separable at the receiver. Okay. And to see that is the case, we take two signals, for instance, this signal and the green signal here. And these two signals are orthogonal to each other, meaning that if we take the product of them and integrate, we get 0. And that means that we can use linear techniques to filter out the green and the blue pulses, even if they overlap. Okay, and we can figure out the amplitudes of those. Okay. Yes?
In the case where
Okay. No, never mind.
Okay, good. So the thing is that when we add these together, we get a waveform, a purple one. But out of the purple waveform, we can filter out the green one and the blue one without any crosstalk between them, because they're orthogonal to each other. Okay, so code division, this is used in 3G and also in Bluetooth, for instance. LAN bridges, LAN switches, same thing. The idea here is that we have local area networks with some hosts associated with that. And we had another local area network here with hosts like this. Suppose hosts on the local area network 2 would like to communicate with local area network 1 hosts here. We can put in a router if we like, but it's easier to put in a bridge. And a bridge magically works to connect this into logical large local area network. So the bridge here is transparent to the hosts. So the operation of the bridge is invisible to the hosts. The hosts just see a bigger logical local area network. So that's the main idea. So these bridges, they work, they build a routing table. So if there comes a packet here, the bridge here needs to figure out whether this packet should remain on this LAN or it should be bridged over to the next LAN. And it should go to the next LAN, of course, if the destination address in this packet is a host on this one. So how do we figure that one out? Well, we figure that one out by listening to the traffic to identify from destination addresses on the frames to which port from the bridge perspective that these hosts reside on. And we build out a routing table from this. So the bridge eventually, by listening to data traffic, can figure out from the destination address if it should be switched over to the other one or not. If it doesn't know anything, it switches it over automatically, just to be safe. So this backwards learning is used in order to build this routing table. It's actually called a forwarding table, so it's not it's actually not a routing table, it's a forwarding table. So this is done by this backwards learning mechanism. I showed that in a lecture a few times ago, how that works. We also use a spanning tree protocol, and that is to prevent that we have loops in the topology. Because if somehow we add another bridge like this, then we have a loop here that the packet can go this way, and then go back this way, and then go back this way, and can keep on running around there in circles for a long, long time without ever dying, and this is not desirable. So this spanning tree protocol is a way for the bridges to figure out which of the connections the bridges have to the LANs should be enabled and which should be disabled. Okay. So look at the lecture there and you can see how that works. Security, we already talked about that last one, so I'm going to skip that now. It's a part of the course, so don't forget about that. Whew. So that was the course. I don't know about you guys, but I'm tired. So, but we have 15 more minutes, so let's spend them wisely, and then we can say it's enough for this week. So do you guys have any particular questions of material that you would like me to somehow talk about? What is the most difficult part of the course that you still are unsure about how it works? Or everything is so crystal clear you don't even have to study for the exam? There is a third option also. I'm totally confused, I don't know what to ask. No, I know how it is, right? But maybe you had something that was nagging you, right? Okay, I don't fully understand this. Maybe we can talk about that. Anything? Okay. I'll ask, yes?
How deeply do you have to understand the input checksum and CRC?
I think you should be able to compute them, right? Yeah, so, and then but you know exactly how to choose the polynomials for the CRC, no. So that you don't have to do. Anything else? I'll ask once more before we finish, right? And then I can just talk about what comes next now. So now, when do you select master programs? Within sometimes in April, right? So there's still some time to consider this, and of course, all master programs would like you, especially you, to join their program, right? You in particular, right? So there is a little bit of competition between the master programs, right? So, but so I know I have a master program that I care about mainly, but of course you should take what I say with a grain of salt because I'm biased towards this, obviously, right? I just like this topic so much. So the one is MPCOM. So people in my group teach in this, and we have been responsible for the curriculum here and so forth. If you look at the course evaluations in this program, you see that they are very good. Right? So it's a good program. However, if you're not interested in this, you should not go. You should not take the program, right? But if you're interested in the general area and would like to have nice courses, this one is to be considered. If you're more interested in, you're still interested in communications, but more on the higher layers, like you know, more towards computer science, computer engineering, there is this MPNet program. If you're more interested in hardware, then the wireless photonics and space program is more for you. So this is more like devices, building radio, receivers, transmitters, things like that, hardware stuff. If you take MPCOM, you can take courses in this program. If you read MPWPS, you can take courses in here. So there is a little bit of overlap here. But if you know your focus is on hardware, you should go here. If you know your focus is not on hardware, but you know, physical layer and data link layers, you should go here. If you want to talk IP, you should go up here. If you're even more interested in hardware, then there is this one, which is more on the digital side, I would say. So, and this is certainly part of communication systems. All the digital hardware, analog hardware makes up, you know, devices like this. So, actually, competence is needed in all parts here in order to construct something like this. And of course, you need also all the mechanical skills and whatever, right? So it's a complicated product. Design, right? How to design a new adapter. Yeah, and many things. How to make money. Okay. If we look at MPCOM, here's the promotion slides, enabling the interconnected world, right? So what does that mean? Well, it means you know, cellular phones and things like that, internet access, but that's only part of it. If you follow what's going on today in society, this intelligent transport system, self-driving cars, they would need communications. Smart cities, what are those? Well, cities where people can live and breathe fresh air and, you know, have all the amenities we would like to have. Traffic safety is of course important. Positioning in navigation, something that we would like to have everywhere. E-health, we talked about that. Industry 4 is more like this process control, how to build efficient production systems and things like that. All types of cloud services, you know. So if one follow this program, what type of career opportunities are there? Locally here in Gothenburg is of course things that you might want to believe that the main employer is Ericsson. That's not really true. They employ a lot of people, but there are many others that are looking for people that knows communications. Huawei has a small operation in town. It's a competitor to Ericsson, but a global, very big company, bigger than Ericsson. Volvo Cars and Volvo Trucks, of course, the vehicular manufacturers. Communication is very important for them. Sinuity is a joint venture between Volvo Cars and Autoliv. Autoliv is a supplier of safety stuff. Anything from radars to vision sensors to airbags and seat belts and things like that. So Sinuity is a joint venture between Volvo Cars and Autoliv. It's an exciting new company here in town. Ruag Space up there in, what's it called? I lost the name. You see a big rocket next to Road 40 on the way out to Landvetter. That's Ruag Space. Saab is next door to Ruag Space. They do defense stuff, radars mainly, but other things here also. ABB is a process control. And then there's a bunch of smaller companies, and I just put down Camcom here because it's one of my former PhD students who started this company, which is now quite big actually. And then if you don't want to go to industry in Gothenburg, of course there's industry elsewhere too. It's a global market. If you want to continue into PhD studies, for sure we have PhD students in my group from this program, and the PhD students the people from this program, their PhD studies elsewhere, both in Sweden and internationally. Okay, so life is, or career opportunities are good, I would say. Specialization packages, there is some recommended ways to go through the program, depending on what your inclination is. I won't go through this. You can see this in the details. Yeah. All right, so MPCOM, right? Yeah. So any other questions now? Exam? Things like this?
It's a question about not MPCOM but wireless. Kind of in between that. If you look at the 5 obligatory courses for MPCOM, how is it? Do you know if you can choose to go to them as well if you go to, for example, wireless?
If one can go for the mandatory ones in MPCOM. I don't think there is space enough to do this, but you can maybe take them as extra courses. But you know, it's been a while since I was involved in the planning of the MPCOM and in the master programs. So look into the study guide. Look into this mpcom.se. There is a folder that explains how things work, what freedom you have, and you should find a similar folder for the wireless program. Okay. Any other questions? So maybe we should break tradition then and finish early. Right. It's been a pleasure teaching this course. I'm sorry for not being able to write on the blackboard. I hope it was okay doing it this way. Yeah, question?
How late before the exam can we send in questions at latest and get
15 minutes. Nah, I don't know. The Thursday, I'm planning to go to this big seminar. It's one of this area of advanced ICT has an initiative seminar. So I will be offline on Thursday, which is the same day as the exam. But otherwise, until then, 23:59 Tuesday. Okay. Anything else? Okay, it's been fun. Good luck on the exam. Study hard. Please fill out the questionnaire. All right.